Hello, I Anand Jain welcomes you to your favorite Shridevi classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today we will remove your doubt and confusion when we discuss one probable board exam question pattern in senior secondary physics examination, and our topic is coefficient of self-inductance, and we'll find out self-inductance of a coil and solenoid, and we'll discuss the concept with clarity. So let's start. An inductor is a two terminal coil configuration which can store energy in magnetic field. Inductor got a property known as inductance, and due to inductance, an inductor opposes the changes of current magnitude flowing in it. Often inductors are formed from coils of wires around a high permeable ferromagnetic material that may be iron, steel, nickel, cobalt or ferrite. Now when current passes through such inductor coil, number of turns multiplied by current become magnetomotive force mmf, and that mmf in magnetic circuit establish flux, and as per Ohm's law of magnetic circuit, mmf is equivalent to voltage, and opposition to flux flow of magnetic circuit is known as reluctance, and ratio of mmf to reluctance will become flux in magnetic circuit, and flux produced by any inductance, as mmf is product of number of turns and current, is directly proportional to the current which is flowing through the coil. So a coil produce flux around it proportional to current which is flowing through it. If current is steady in magnitude, flux produced by such inductor coil is also steady in magnitude, and in that case inductance property remain ineffective. The physical property of coil or inductor, that is inductance, comes in effect only when current is time varying. When current changes, it also produce changing flux proportional to current. So time varying current excitation in an inductor coil produce time varying flux, and that flux links with the turns of coil, and time varying flux linkages with any coil generate induced EMF in such coil. Since flux is proportional to current, so we can say induced EMF in coil is directly proportional to rate of change of current with respect to time in such inductor coil. So when current change with respect to time, as per rate of change of current with respect to time, there will be some induced EMF in coil configuration, and as per Lenz law, this induced EMF due to change of current in it oppose the cause, that is changes of current taking place in coil configuration. So inductor generate a self-induced EMF within themselves, and as a result of that, this coil configuration opposes the changes of current taking place in coil configuration. And to manage continuously the time variation of current in such inductor coils, we have to apply a counter source voltage equivalent to induced EMF, and as induced EMF is directly proportional to rate of change of current with respect to time, so we can say in an inductor, to maintain time variation of current, we need a proportional voltage across it, and this proportional relation between applied voltage and rate of change of current with respect to time can be converted into equality using a constant capital L, that is called coefficient of self-inductance, and this capital L self-inductance is measured in Henry unit. So in an inductor of L Henry, to make di by dt current change with respect to time, we have to apply a voltage V, or there will be an induced EMF E equal to L di by dt, and from this we can get the definition of self-inductance. Self-inductance of a coil in Henry is that induced EMF in volt which is produced when current is changing at a rate of 1 ampere per second in a coil. So when di by dt is 1 ampere per second, whatsoever induced EMF or applied voltage is the self-inductance of coil configuration. This numerical will explain application of V equal to L di by dt relation. We have given a coil of 0.2 Henry. So this 0.2 Henry is value of self-inductance, and 10 ampere current is flowing in it. And if current reverses in a linear manner in 10 millisecond, that means from one direction 10 ampere current, it become 10 ampere current in opposite direction in 10 millisecond. We have to find out induced EMF or voltage which is applied across it to make that current change. in the coil. So here the duration for current change is 10 millisecond, that is in second 0.01 second, and the amount of current change di is from 10 to negative 10, so this change is 20 ampere. And if we substitute V equal to L di by dt relation, the value of L as 0.2 Henry, di as 20 ampere, dt as 0.01, and solve it, we'll get that induced EMF or applied voltage is 400 volt. Let's understand the dependence of coefficient of self-inductance. We know induced EMF in a coil is rate of change of flux linkages in it. So it is dN phi by dt, and this is also L di by dt. Now if in the same dt time interval with change of di current, the change of flux linkages is delta n phi, then self-inductance is change of flux linkages divided by change in current, and we can say self-inductance is change in flux linkages per unit change of current. Change is second value minus first value, and change of current is I2 minus I1. And if initial value is taken as 0, since current and flux are proportional to each other, for 0 current flux is 0. So we can say self-inductance is flux linkages per unit current. It is ratio of flux linkages. Flux linkages is flux multiplied by number of turns in coil divided by the current in coil, become the self-inductance of coil configuration in Henry. If for a given current we have higher amount of flux linkages, higher would be the value of self-inductance. So here in this relation L equal to N phi by I. This L is self-inductance of coil in Henry, N is number of turns in coil, phi is flux produced by coil turns when I ampere excitation current is passing through coil turns. Now from this definition of coefficient of self-inductance as flux linkages per unit current, we can say since current and flux are proportional to each other, so their ratio of flux to current doesn't depend upon magnitude of flux or current. So self-inductance of any configuration doesn't depend upon amount of current or flux produced. If we double current, flux will also double, and for that configuration, coefficient of self-inductance will remain the same. Several identical turns wound on certain axis with little axial displacement form a configuration known as solenoid, and we have to find out coefficient of self-inductance for such solenoid configuration. So here on L length of solenoid we have wound n number of turns, and cross section area of solenoid got a value a meter square, and the core, the material inside coil turns, got a relative permeability mu r or permeability mu equal to mu 0 mu r. We know for a magnetic field intensity H, the magnetic field flux density is given as B equal to mu H, where mu permeability of core material is permeability of air multiplied by relative permeability of core material, and magnetic field intensity is mmf per unit length. Mmf is product of number of turns and current flowing through those turns. Now flux across core cross section area A is given as product of field flux density multiplied by core cross section area, and in place of B we can write mu H, and in place of H it is mmf per unit length. So flux is mu 0 mu r Ni over L multiplied by area, and we know coefficient of self-inductance is flux linkages per unit current. So when for flux linkages we have multiplied this by N and divided this by current I get cancel out, and we got a relation for coefficient of self-inductance as mu naught mu r n square area divided by length, and this expression clearly indicate that coefficient of self-inductance won't depend upon value of current or flux, as the two are proportional to each other, and the ratio calculation become independent of value of current and flux. And self-inductance depends upon number of turns, as self-inductance is proportional to turn square. So if we double number of turns in a coil, the self-inductance will become 4 times, and this L upon mu 0 mu r A can be given another name known as reluctance, opposition to the flow of flux in magnetic circuit. And we can derive the similar relation by another way. Self-inductance is flux linkages per unit current, and as per Ohm's law of magnetic circuit, flux is mmf divided by reluctance. And when we make ratio calculations, flux proportional to current, and in denominator there is current get cancel out, and coefficient of self-inductance become n square by reluctance. So coefficient of self-inductance is directly proportional to square of number of turns in solenoid and is inversely proportional to reluctance of magnetic circuit. For a magnetic circuit having turns in coil N and reluctance for magnetic circuit capital S, the coefficient of self-inductance of N-turn coil is given as N square by reluctance. And for a simple magnetic solenoid circuit of length L, area of cross section A and relative permeability mu r, the reluctance is given as directly proportional to length, inverse proportional to area of cross section and inverse proportional to relative permeability as this expression. And in expression of coefficient of self-inductance, which is flux linkages per unit current, and in place of flux when we write mmf over reluctance, mmf is product of N and I get cancel out and this expression become N square by reluctance, and in place of reluctance we can write L upon mu A, and simplification result as coefficient of self-inductance is equal to mu naught mu r area N square divided by length of magnetic circuit. So we can say coefficient of self-inductance is directly proportional to square of number of turns. If we double number of turns, coefficient of self-inductance will become 4 times, and coefficient of self-inductance is also directly proportional to relative permeability of core media. And if inner core of solenoid is made of some ferromagnetic material such as iron, steel, nickel, cobalt or ferrite of higher value of mu r, the coefficient of self-inductance greatly increases in direct proportional of relative permeability. So in place of air, if we put iron of relative permeability 2000, the coefficient of self-inductance will increase by 2000 fold. Let's find out coefficient of self-inductance for a plain circular coil. So we are given a plain coil of N turns and R radius, and when it carry current I in turns, at its center magnetic field flux density or magnetic induction is given as mu 0 Ni over 2R Tesla. And if we assume that flux density is uniform all around this inner area of coil, the total flux passing through coil inner area is flux density multiplied by cross section area of coil, and in place of flux density when we substitute mu 0 Ni over 2R, area of this circular coil of radius r is pi r square, 1r get cancel out and flux will become mu 0 pi r Ni over 2, and we know coefficient of self-inductance is flux linkages per unit current. So in flux when we multiply with number of turns, this N become N square, and when we divide by I, this I get cancel out and coefficient of self-inductance results as mu 0 pi N square r over 2. And for constant radius we can say coefficient of self-inductance is directly proportional to square of turns. So with same radius, if number of turns are doubled, coefficient of self-inductance will become 4 times. And similarly, for same number of turns, coefficient of self-inductance is directly proportional to radius. There are some tricky questions which may be asked in our examination. One is this: with given wire length, if turns in a plain coil are doubled, what will be the new self-inductance of that coil? We know that one circular turn of r radius got a periphery 2 pi r, and for n turn coil the total wire length is 2 pi r n, and when wire length is the same or constant, then the product of number of turns and radius of coil remain constant. So here self-inductance, which is proportional to square of turns multiplied by radius n square r, this could be written as nr multiplied by n. Nr is constant for given wire length, so we can say self-inductance for given wire length is not proportional to square of turns, but it is simply proportional to number of turns, and when number of turns are doubled, self-inductance with given wire length also get doubled. Another question: with given wire length, if coil radius is doubled, what will be the new self-inductance? So again, for constant wire length, product nr is constant and coefficient of self-inductance is proportional to n square r, and we can write it n square r square over r, and r product is constant, so this n square r square is also constant. So coefficient of self-inductance is inverse of radius of coil, and when radius get doubled, coefficient of self-inductance become half. We hope this beautiful learning video has solved one of your board examination question, and now you can score better marks in that examination. If you found our study work valuable, you can also refer notes for the same, and solution of this problem and other important problem is given in description with a link. You can use that in your study or share that to your friends, as when you spread knowledge, you increase your knowledge. Happy learning. Have a nice time. Thank you very much.